Okay, so our first speaker today is Chris Bourne from Tohoku University in Riken, and he's going to talk about, well, we'll see. We'll see.
Sure. Yeah, thanks very much for the invitation to talk. I'm quite happy to be here, even if the time is not exactly ideal for myself and others in Japan, but well, we'll deal with it. So yeah, today I want to talk about, in some sense, kind of an old story, this classification of free fermionic topological phases. But I want to do it both from the perspective of KK theory, but also because this workshop is about particularly geared towards the case of these symmetry protected topological phases and higher order interactions. I want to, as much as possible, kind of do this from the perspective of like gapped ground states and the higher order picture, even though eventually we will make a sort of a free fermionic type assumptions and approximations. Okay. So, we only have 45 minutes, so I'll only give the very, very well, not even an introduction really to KK theory, but just a kind of an outline of some of the elements that come into K theory or KK theory, and how some of these things arise relatively naturally in things that people often encounter. And then I'm going to talk about these so-called quasi-free gapped ground states. So Peter yesterday taught us about gapped ground states with spin chains. We're going to look at the fermionic case, and in particular, a very sort of special, sort of easy class of such ground states, these quasi-free ones, and then we'll sort of tie these two things back together. And I will almost certainly not get to it today, but I guess, so in the chat, I put the slides for the PDF of my slides. And if you want, maybe just in your own time, you can, if you want to read more about KK, I put some extra things in there, which I guess I cut the time. Okay, so yeah, so the KK theory, it's a lot of things, right? But in particular, it's this bivariant functor. So if I have these two separable Cstar algebras, A and B, then we can define this abelian group KKAB. And it encompasses a lot of things that at least hopefully some of us are familiar with. So for example, if you have an A in the right-hand slot and Clifford algebras or complex numbers in the left, and you recover the K theory of a Cstar algebra. So Nigel talked a bit about these things yesterday, and if you prefer topological K theory, then if you put continuous functions on a compact Hausdorff space and you do the same thing, then you get topological K theory back. And similarly, okay, if I put things on the left-hand side, but with complex numbers on the right, then I get the algebraic dual of K theory, which is this K homology, which probably people are less familiar with, but there's still lots of interesting things that one can say about K homology. So, as was kind of alluded to yesterday, really what's kind of this central and powerful part of this theory is this this associative internal product structure, which I'm not really actually going to use today, but it seems remiss to not at least briefly mention it, where if I have an element in KKAB and an element in KKBC, then I can sort of cut out this middle variable and I spit out something in KKAC. And this product is, as Blackadder says, it's a functorial in all possible senses. And maybe one way to think about elements of these groups and how this product works is, for example, if I have something in the K theory of A, then I have something in KKCA. But if I also have something in KKAB, then I can use this product structure. And then just following this, this product, then I'll get something in KKCB, but that's just now the K theory of B. So if I have an element in this KK theory group, then it gives me a way to actually map between what could be in general the K theory of quite different Cstar algebras. So it's really quite a powerful technique to sort of pass between different areas. Maybe you're passing from a space to its boundary, or a subspace, or an entirely different space entirely. So these are some of the things that, well, the point is, okay, if you have an element in this group, then it really does give you a lot of flexibility to pass between different homology theories. Yeah, you can obviously do the same thing on K-homology as well. Okay, so what is this group, or how do you define this group? I'm not going to give a precise definition today, but essentially the things that build this group are these things called Kasparov modules. I think Kasparov module is actually the correct pronunciation, which is a triple of 3 things, which I'll only kind of vaguely define. So the first is this EB, which is a so-called right Hilbert Cstar module. And we also want it to be Z2 graded, but I will not focus on this too much. So I'll define at least some of these points in the next few slides. So we have this so-called Cstar module. I'll say more about that soon. We have a representation. So, we have our algebra on the left A, and that should act on this Hilbert Cstar module. And then our final ingredient is a sort of elliptic type operator, but it's now a sort of a generalized notion of elliptic, because again, we're not necessarily acting on a Hilbert space anymore. It's now operators on Cstar modules. Okay, so these are the ingredients that go into defining one of these Kasparov modules, which then gives you elements in this KK-theory group. So yeah, I'm mostly just going to give a few examples, and then I'll move on. So first, okay, what are these Cstar modules? I think they came up slightly yesterday in the discussion, but okay, so a Cstar module should first of all be a module, right? So, and because Cstar algebras are not necessarily commutative, we need to just clarify whether it's right or left. We're only ever going to look at right modules. So we have an action, so we have a linear space and a right action of a Cstar algebra B. And the important other point is that we need a sort of a B-valued inner product. So a sesquilinear pairing from the linear space to B. And this pairing should satisfy things that look like kind of a Hilbert space, but sort of switch to a Cstar module instead. So, when I flip the order of the inner product, then rather than taking the complex conjugate, I take the adjoint of the algebra. And similarly, it should behave nicely with respect to my action. So this E2.B means the right action of B on E2. I should be able to pull that out. Yeah, this E applied to itself in the inner product should be positive, where now positive means positive as an operator. So it should have positive spectrum. And I can use the fact that I'm landing in that when I apply this inner product, I land in a Cstar algebra, which comes with a norm. So that gives me a norm on this module, and it should be complete with respect to this norm. So there are actually other properties as well, but these are sort of the essential ones which highlight the difference between a Cstar module and Hilbert space. But of course, for example, if I just take the complex numbers, which is a perfectly reasonable Cstar algebra, if maybe a little trivial, then a Hilbert Cstar module for the complex numbers is just a Hilbert space, and the inner product is just the inner product. A slightly, but only slightly more non-trivial example is where I take just the algebra B itself as the vector space, and then I just define a right action by right multiplication. And then I define an inner product by, again, multiplication, but because it's sesquilinear, there's an adjoint on the left. So these are two very simple examples. I have more, so let's continue, I guess. So maybe one that is more familiar to people is take a compact Hausdorff space with a complex emission vector bundle with finite rank. And then what you can do is you can look at the algebra of sections, just maps from the base to the fiber. And this section algebra you can equip with a right, or actually it can be left as well because this algebra is commutative, C of X module structure, because this is a perfectly reasonable Cstar algebra. And the right action is just right pointwise right multiplication, and I use the Hermitian structure of this vector bundle to give me my sort of C of X valued inner product, where I just take the Hermitian inner product at pointwise. So another example is take a unital Cstar algebra and take a projection in the matrix, n by n matrices over this algebra. And maybe an example would precisely be the Fermi projection of a gapped Hamiltonian in the one particle framework. Then what you can do is I can, with this module that I built over here, just from the algebra over itself, I can take n copies of that. So a freely generated module of finite size, and then just hit it with this projection P, and I get a finitely generated and projective Cstar module, where it's kind of, the structure is as you would expect, where when I act by the right, I just sort of act diagonally by this formula, and I just sort of do the usual sort of inner product type formula, where it will be B, Bn, P, C1, just sort of this type of formula. And of course, if you're familiar with the Sayre-Swan theorem, then actually this first example is a special case of this finitely generated and projective module, precisely because if you have a finitely generated and projective module, then this section algebra, you can always write as a module over C of X. It's isomorphic to some finitely generated and projective module where P is an n by n matrix. Okay, so these are a few more examples of Cstar modules. So we want to talk about operators on these modules. And rather than bounded, we actually want to talk about adjoinable modules. So we have this inner product, and we're only ever going to want to consider operators that act on this space such that there has some adjoint with respect to this inner product. So if you have this, then this operator will be bounded. It will be right linear in the sense that T E dot B is T of E dot B. So it will respect the module structure as well. So we're just going to only ever look at these so-called adjoinable operators. So a good example of these adjoinable operators are these finite rank sort of Kep-Bra type operators, where if I have E1, E2, and E3 from my module, then I can take the inner product of E2 and E3. That gives me an element in B. And then I use the right action and act on E1. So this is sort of an analog of a finite rank type operator. And you can check, it's a simple calculation that this guy is in fact adjoinable, and the adjoint is just the same operator with the E1, E2 reversed. So what you can do, sort of similar to a Hilbert space where the finite ranks generate the compact operators, you can precisely just declare that the compact operators on this module, I just take the algebraic span of these guys for all the possible E's in my module, and take the norm closure, the operator norm closure. Okay, so if I go back to the example of the finite rank vector bundle and the Cstar module there, then because we're in a compact space with a finite rank vector bundle, then actually the compact operators on this Cstar, on this module, the C of X module, coincide with the adjoinable operators. And in particular, you can quite easily characterize these operators as kind of what you would expect. These adjoinable operators are just the sections of now the endomorphism bundle. So it sort of lines up with what you would expect for an adjoinable operator on this section algebra. So on my other sort of simple example, when I have just the module over of B over itself, then it's very easy to check that the compact operators, just using how the action works, that will just generate B back. And the endomorphisms, the adjoinable operators, will be the so-called multiplier algebra. So, in the same way that when you have a non-compact space, there are lots of different ways that you can compactify. When you have if B is a unital Cstar algebra, then the multiplier algebra is just B. But if B is a non-unital Cstar algebra, then the multiplier algebra is, in some sense, the biggest unitization that you can have. So it roughly corresponds to the Stone-Check compactification. In the commutative case, it does correspond to the Stone-Check compactification. So it's a very big compactification in that sense. But I mean, if your algebra is unital, then this thing is just going to be equal to B again. So if you just want to focus on unital Cstar algebras for this talk, then that would be not a problem, I would say. Okay, so let's build some examples of these Kasparov modules from what we've learned. So when we have this finitely generated and projective module, then recall we needed three things. We needed an algebra, a Cstar module, and an operator. But in the case where B is unital, where everything just now acts as compact operators, then I can actually kind of ignore this last step of needing a elliptic self-adjoint operator. And so I can instead just take the module of the finitely generated and projective module, the complex numbers on the left, just 0 as my operator. And that gives me a nice class in this KKCB, which is the same thing as the K-theory of B, and precisely furnishes that isomorphism between the K-theory and KKCB. So another example, which is going to actually be a little bit important later, so is the case where you have a unitary element. So again, Nigel yesterday talked a lot about projections and unitaries. These are useful things that we want to consider for Cstar algebras. So take a unitary element in matrices over B or just over B. So it has this formula. So in particular, maybe this unitary comes from a Hamiltonian that looks like this. So it has one of these sort of spectrally flattened chiral symmetric Hamiltonians. Maybe it's not, but I mean, okay, just take a unitary. So to define these KK or these Kasparov modules, we need this self-adjoint elliptic operator. And so we need to build a self-adjoint operator from a unitary, but we kind of know how to do that, at least in the Hilbert space case, which is if you have a unitary operator, you can take its inverse Cayley transform and you get a self-adjoint operator. And we can do the same thing in a Cstar module now, where I define the so-called inverse Cayley transform of this unitary. So it is this operator here, but now this actually now acts on a Cstar module, and in particular, so it's actually unbounded. So it has a certain domain, because clearly this might cause problems, this U-1 inverse. So it's going to act on, in general, some submodule of the finitely generated guy. So we can use this operator to build another one of these Kasparov modules. The only other thing we have to now worry about is this Z mod 2 grading, but we easily kind of just deal with that we just take two copies of our Cstar module, and we just declare, okay, one is the even part, one is the odd part, and then we just put this guy as an off-diagonal operator. And then to deal with the fact that we've doubled up, we also put a Clifford algebra here, which is going to act as -1, 1. So you're just using the Pauli matrices. So this will give us a class in this KK Cliff 0, 1B, and that is the same as the odd K-theory of B. And again, this is how you map between unitaries and Kasparov modules in general. Okay, so that was a very brief introduction to KK theory. I'm now going to very move to more sort of physically motivated things for a while, but we'll come back at the end, hopefully, if it's time. So I'm now going to talk about, fermions and ground states and these sorts of things. And the way I'm actually going to do it, which is going to be maybe a little bit different to the way that people are familiar with these free fermionic systems, is I'm going to work in the Nambu space of field. So this is kind of a Hartree-Fock mean field type approximation of a free fermionic system. So, you have your particle space and your hole space, which is useful for modeling superconductors, for example. And so, well, okay, one way to think about this is I just have a complex Hilbert space, but then I also have this real structure, this gamma, which maps particles to holes. So it's an anti-unitary self-adjoint operator. So it squares to 1, but will anti-cubic with I. And so I'm going to work with fermions. So I'm going to work with, but in the algebraic framework, so I'm going to work with the CAR or CAR algebra. But for the self-dual picture, where I'm in the Nambu space, I actually work with this thing called the self-dual CAR algebra, which, if you very roughly, corresponds to a Majorana type representation. So this self-dual CAR algebra is the Cstar algebra, which generated by the identity and these field operators, these C of V, where when I take the adjoint, I pick up this gamma in here, and I satisfy these kind of Clifford algebra type relation. So yeah, if the space H is finite dimensional, then this is going to be isomorphic to a Clifford algebra, but I'm going to just work directly in the infinite systems here, or just assume that we have an infinite dimensional space. So this doesn't really look like what people know to be the CAR algebra, right? But you can recover the sort of more regular CAR algebra when you have one of these things called a basis projection, which sort of splits your Hilbert space, this complex Hilbert space, into 2 parts, precisely the particles and the holes. So if I have a projection which satisfies this property, so P plus gamma P gamma gives me the identity, then when I restrict these operations to just half of this space, this pH, then you'll see that the usual sort of CAR relations reappear. So you sort of identify the annihilation operator with C of PV and the creation with C of gamma PV. And in the same way that the CAR algebra is graded, this self-dual CAR algebra is also a Z-mod 2 graded algebra by this parity operator, where we just say that, okay, any generator which is not the identity is odd, because it will add or remove particles. Okay. So again, we're just looking at free fermionic systems. So in particular, I'm going to focus on these so-called quasi-free pure states, which is, again, very roughly speaking, this kind of Hartree-Fock mean field approximation, which is where we build a state from just a 2-point function. So when you have one of these basis projections, so a projection that satisfies this relation, then you can build a state on your Cstar algebra, where it's a positive linear functional. By first, you just act on 2 elements that look like this. By CU star CV, I just take the inner product in the Hilbert space with UPV, and then I can extend it to the rest of the Cstar algebra by just declaring that this vanishes on odd products of elements, and on even products of elements, then I just get a certain sum of permutations of elements that look like the 2-point guy. I didn't write down the explicit formula because I don't think it's particularly illuminating, but it's a sum of permutations of, so it all just comes from this 2-point function. So, the theorem, which was, very old now, from 1970 due to Araki, is precisely that. Okay, first of all, when I have a basis projection, this is a pure state, so it's a unique, or it's an extremal point. And when I have 2 basis projections, then these 2 different states that come out are going to be equivalent or unitarily equivalent if and only if the difference of these basis projections is a Hilbert-Schmidt operator. So this is kind of a algebraic version of the Charles-Stein-Spring theorem. So yeah, it's something that appears in when you deal with Kerr algebras over infinite dimensional Hilbert spaces, right? Is that you actually have uncountably many inequivalent pure states. So one sort of useful point about this self-dual Kerr algebra is that it gives you a way to kind of, within a single Hilbert space, compare different potentially equivalent or potentially inequivalent representations of your regular Kerr algebra. So, one nice thing about these quasi-free states is that when you look at the GNS representation, so usually this is a bit of an abstract construction, but for these quasi-free states, this is actually a very relatively concrete. So when I had this state on this Kerr algebra, then the GNS representation that comes from this state. So okay, first of all, the GNS Hilbert space is really just the fermionic Fock space. So where I use this hat or wedge to denote the antisymmetric tensor product, where the the creation operators really do act as creation operators, and this vacuum element is precisely kind of the vacuum, because this gamma 0 pH is just the linear the one-dimensional space of this vacuum state. So this GNS representation is in general quite an abstract construction, but for quasi-free pure state, or for these quasi-free Fock states, it's kind of what you would expect. It's essentially just the second quantization, but restricted to the to the pH. Okay. So we have these states, but we also, we want to talk about ground states, right? And again, we're just dealing with free fermionic cases. So this all just comes from the single part or the Nambu space. So we start up with an operator H, which ideally is coming from maybe some quaternionic interaction, quadratic interaction, which needs to have this, you might call it a particle symmetry type relation. So it needs to anti-commute with this real structure. But if you had that, then you can easily define a dynamics or a time evolution on your self-dual Kerr algebra by just taking the time evolution of the vector inside. And you can see then why you need this condition, right? Because we want this e to the ith to commute with the real structure. So, so in general, this is just true for any old Hamiltonian that satisfies these relations, but we want to talk about gapped ground states, right? And the nice result is that precisely when you have an invertible, the so-called BDG type operator or Hamiltonian, then you can build a basis projection just by taking the positive spectral projection of this operator because of this relation. The gamma will map positive energies to negative energies. So I just need only 1/2. And I get a basis projection, and in particular, the quasi-free state that is built from that basis projection is a gapped ground state for these dynamics where, so yeah, and I mean gapped ground state in the way that was defined by Peter yesterday. So it's a ground state in the sense that, this equation holds, so the sort of infinite dimensional formulation, and gapped in the sense that the generator of the dynamics on the GNS space, this positive operator has a gap, spectral gap above 0. I mean, this is actually very easy to show. Yeah, sure.
If you go one slide back, the GNS representation, was it with respect to the self-dual Kerr or with respect to the Kerr?
This is actually, so yeah, this guy is isomorphic to the self-dual, right? But here I'm talking about the regular Kerr. Obviously, there is also a somewhat equivalent GNS space for the self-dual car, but it's, you know, this looks a bit more familiar to people, I would say.
Yeah, but in the next one, you seem to define the state for
here I'm back in the self-dual
car.
picture. Here I'm back in the self-dual, that's true. But I mean, again, so the self-dual car, once you have a basis projection, is isomorphic to a particular car algebra. So I am sort of being a little bit ambiguous in terms of, you can sort of pass back and forth between them.
Okay.
If you're happy with that.
It's maybe,
yeah.
I'm not sure how basic this question. If you look at the generator of alpha, can you characterize it a little bit? Maybe spectrum. As I will assume, it's not necessarily that if H straight has a gap in the spectrum that the generator of alpha will have a gap in the spectrum.
I mean, we just need this invertibility condition of this H,
on the
precisely
one,
because yeah, I mean, because, you know, you're building this GNS space very, you know, roughly speaking, from the second quantization of this guy, but restricted to only the positive energies. And because you're starting out with a gap, then you'll sort of keep that gap. Okay. So one just point of note is that, you know, this operator H, this anti-commutes with the gamma, but if I look at its sort of spectral flattening and then I hit it with an I, then I get this skew adjoint unitary J, and this one will commute with the real structure, and I'm going to use this later. Okay, so I now want to talk about symmetries of the ground state. So we're just going to start out with a unitary or anti-unitary operator again on our Nambu space, but it needs to commute with the real structure, so it should restrict to a representation on the real subspace of elements that are fixed by a gamma. And again, you can define this sort of quasi-free type action where I just hit where I just act by a W inside of the field element. And yeah, so if you have one of these unitary or anti-unitaries and they commute, and it commutes with gamma and it also commutes with H, then this is also then going to be a symmetry of the ground state. So the ground state will be invariant under this automorphism. Okay, it will be invariant if it's linear, and it will have this sort of star relation if it's anti-linear. But this is what we want for invariance of an anti-linear automorphism with respect to a state. And this is in some sense where the Nambu space picture differs from the usual kind of Kitaev or Ludwig Fudosaki Schneider classification of free fermionic systems, where there you have these, you know, particle hole type symmetries or these chiral type symmetries which can commute or anti-commute. But here, if I want something that conserves the ground state, then it needs to commute with the Hamiltonian. But I mean, these pictures are actually equivalent. It's just, this is just how these symmetries work in the Nambu space formalism. So
sorry, Chris,
in particular,
can I ask a question before you proceed? So at this point, what is the essential difference between a Majorana formulation? Because it seems essentially it's almost identical.
I mean, this self-dual picture is more or less the Majorana type representation, yeah.
Right, okay. So, okay, no, well, then yeah, that's fine, thanks.
Okay, cool. Okay, so in particular, this was just for any old unitary or anti-unitary, but you know, I don't know if Martin is here or not, but you know, these Outland and Zirnbauer, they specified certain what they describe as physical symmetries, and how these are all described in this Nambu space setting was sort of outlined in this paper by Kennedy and Zirnbauer from 2016 in CMP. So again, we have all these symmetry type operators. And again, so all these operators are actually going to commute with my Hamiltonian. And so these are the sort of symmetry types classes and the operators that can appear. I've not really gone into detail about what any of these are, but I mean, just for example, as an example, the case of a time reversal symmetry, that is going to be a so-called anti-unitary quaternionic structure on our Nambu space. So it'll be skew adjoint, it will square to -1, and again, it needs to commute with both the Hamiltonian and the real structure. But yeah, you can look at all these different types of symmetries, and sort of a nice result, or sort of the thing that I'm going to use from this Kennedy-Zirnbauer paper, is precisely that there's actually a one-to-one correspondence between these physical symmetry operators here that commute with H. And when I take this skew adjoint real unitary J, then I can also consider these other operators, which they call pseudosymmetries, these FJs, which anti-commute with J. And so these FJs are skew adjoint, real in the sense that they commute with gamma, and square to -1. So yeah, I didn't really explain what most of these symmetries are and how they, but again, let me just emphasize that there is a way that this is still more, this is an equivalent formulation to the usual Kitaev, Schneider, Fudosaki Ryu, I forgot someone's name, Ludwig, framework, but sort of transposed into the Nambu space picture. But yeah, this is sort of the only thing that I'm going to need, is that we have these skew adjoint unitaries that anti-commute with this with this other skew adjoint unitary J. Okay, so now we're going to, as my title suggested, going to sort of take cue from these SPT phases, or these symmetry protected topological phases, which I did not actually say what SPT was. So in SPT phases, what do we do, right? You fix a reference product state, omega naught, and then we then look at other gapped ground states of omega such that it's equivalent to omega naught in whatever this equivalence relation is in the space of gapped ground states, but not necessarily G equivariantly with the G, which with whatever symmetry that I consider. So this is sort of very roughly speaking the starting point for how one studies these symmetry protected topological phases of gapped ground states. So we're going to do a similar picture here. We're now going to take a pair of single particle Hamiltonians on this Nambu space with the same symmetry type. And we're going to assume that the gapped ground states that you get from these operators are also equivalent, but now sort of the notion of equivalence that we want in the quasi-free picture is just this unitary equivalence. So we're going to assume that they're unitary equivalent, but we're now going to consider what happens if you restrict to sort of symmetric paths, and symmetry also means with respect to the parity as well. So what does that mean, right? If these two operators are unitary equivalent, then this tells me that P0 minus P1 is Hilbert-Schmidt, L2, sorry. So in particular, also J0 minus J1 is in L2. And if you have that, it's then actually quite easy to show that when I look at these J0 and J1, which are the skew adjoint unitaries, then this space of the kernel of just the sum of the two is going to be finite dimensional. So remember that these operators J0 and J1 are going to anti-commute with these skew adjoint operators Fj here. So in particular, these Fj's are going to be have a representation on this finite dimensional space. And I also get an extra representation of just one of the generators, so either J0 or J1, but not both. So I get a so-called ungraded Clifford module with these generators. And you can ask, okay, does this guy extend to a Cliff n+2 module? And if it does, we say that it's trivial. And that equivalence class, which is the same as the K-theory of a point, basically, is precisely the topological obstruction to connecting these two ground states in a symmetric way. Okay. And right, so for example, if this guy is non-trivial, then you cannot, then any symmetric path that will connect these two things such that this holds, the gap, the ground state gap is going to close one way to think about it. And it will close in a way that it can't be lifted either. Okay, so I have 5 minutes, but that actually is going to be enough to now do this more generally, because, okay, this is nice, and it's a nice little characterization of the gapped ground states, but it's a bit coarse, right? Because this invariance is maybe in some sense not so interesting. It's only ever going to be Z or Z mod 2 valued. But in particular, there was no input that I had in terms of dimension or geometric structure or anything like that. So I'm now going to put these extra elements in and get a more refined invariant. So what I'm going to do is I'm actually going to assume now that my invertible H0 and H1 are now an invertible element of a Cstar algebra, actually in particular multiplier algebra, so it's going to be an element of a Cstar algebra which lives inside the bounded operators on this Nambu space, and there also should be a sort of a real structure on this Cstar algebra that is an antilinear order 2 automorphism, which should be compatible with the Nambu space structure. And so before I had this assumption that the two ground states were unitary equivalent, which translated into that these J0 and J1s were close in some sense. And now I need to sort of argue a bit abstractly and just sort of say, we're going to replace this by just saying that the difference of these J0 and J1 should just be an element of the Cstar algebra. So somehow they should some kind of locality condition with respect to this A. But they should still anti-commute with these skewer joint unitaries, which I'm just assuming live within the multiplier algebra. Okay, so once you have that, I can now sort of do what I did before. So, okay, a while ago actually. So you might remember when I took a unitary, I could take its Cayley transform and I could build a Kasparov module. But now I have a pair of skewer joint unitaries. So I'm now going to define a thing called the relative Cayley transform, which, so yeah, now has input as both J0 and J1. And, okay, it looks a bit like a Cayley transform type thing, but it's now going to be an unbounded operator on this Cstar module. So we'll have a particular domain, and I just take the closure of that domain as my module, so it's dense. But what's nice is that much like the Cayley transform is a nice self-adjoint elliptic type operator, this relative Cayley transform is also elliptic type operator. It's actually skewer joint rather than self-adjoint, but that's easily dealt with. But also this operator is still going to anti-commute with my sort of pseudo-symmetries, these FJs, and also one of the J's, in this case J0. Right, and now with my last minute, so all the pieces are in place, so I can sort of assemble everything now into a Kasparov module. So again, I use this relative Cayley transform. I make it, again, I need to double it up to deal with the grading, and I also need to make it self-adjoint. So I put a minus sign on one of them, which again will give me an extra Clifford generator, and it's going to act on this space with these elements acting on the left as Clifford generators, which will then anti-commute with this operator. And that will then give me a class in this KKtheory group. But I mean, if you don't want to worry too much about KKtheory, this is actually just the same as the real K-theory of a certain Cstar algebra, where again, the degree of this Cstar algebra is, or the degree of this K-theory is determined by n, and that n is determined by the symmetry type of the system that I'm studying. So this is basically the construction that's done in this paper by come out of Christopher Max's thesis, but done in a slightly different way. So you can also see something very similar in this paper. Okay, so time is up. So I just have a few remarks, but what I think I'll do is maybe you can just read this at your own perusal, and I will stop there and thank you for your attention.
Thank you, Chris. Very informative talk. And let's have some questions now.
I have a question. So what happens for if you have a pair of ground states with an equivalent for space representations?
Yeah, I mean, there's not much you can say
does your generalization
about it, really.
Okay, so even you can't. So the example where you have A equals to compact operators, for example, is already a slight generalization of what people usually do with these Bogoliubov transformations. So is there some way to get to be somewhat more general and consider inequivalent for representations by?
So when you're in this picture here, where in some sense there's still a kind of a Fredholm condition floating around because I have a finite dimensional space. So very roughly speaking, this element here determines a spectral flow of this path of operators, which connects H0 and H1, which is now a skew adjoint path. And obviously so the spectrum can close, but it closes in such a way that when you go to the full representation, the gap closes, but the states are still quasi-equivalent, actually. So it's not going to be like completely different sectors or something like that. So in that sense, it generalizes slightly because, okay, when the gap closes, I get something that's non-equivalent anymore, but I get something that's still quasi-equivalent. But yeah, I mean, if this condition fails, then you kind of, well, okay, then you have to pass to the more coarser classification methods where you use things like the split property and just properties of sort of the von Neumann closure or something like that. I don't know if that completely answered your question or not.
It does to some extent, yeah. Thanks.
Okay.
I also have a question.
Who's asking?
Johannes.
That was Johannes, I believe.
Sorry.
Okay, Johannes.
I put my video on so that you can see that I'm really here. I'm not a robot. Okay. I was wondering, did I miss something? But in the beginning, we're talking also about automorphisms in this context, right? Or did I miss?
In what context, sorry?
Well, when you defined the GNS representation, and then on this next slide, can you have
this one?
Where you just before the theorem, yeah. What is? I mean, does it really play a role, this automorphism at the end?
For the quasi-free states, not so much, right? I mean, because really you can sort of get everything you need just from the generator, or the generator on the Nambu space.
Because I was thinking on Emil's question yesterday, whether it seems that if we could sort of pull everything which we do for these vacuum states up to this automorphism somehow using KK theory, but it's not going to that direction.
I mean, not at this point, no. But I mean, you are correct that though, when you want to then now consider the cases with interactions that, yeah, precisely the way in which automorphisms work together is going to play a much more substantial role, which is actually related to this remark here, but because this kind of idea is a way in which you can generalize some of these ideas to the case of non-quasi-free or interacting ground states as well, but it relies on knowing a lot about certain automorphisms.
Okay.
Chris, can you take us through, for example, class A?
I mean,
if I see here that you work with the algebra of compact operators, you will get 0 in that case, isn't it? Because then the multiplier algebra will be B of H, the K theory is,
so the algebra will be the compacts, which is, and yeah, the multiplier algebra is B of H, but the algebra, but the place where I land is the K theory of the compacts, so it will be Z. It will be Z.
okay. That's a good, okay, good pointer.
Yeah, when you have these complex symmetries here, I didn't discuss it, but when you're in this type of symmetry type, then you can actually do a reduction in such a way that you no longer have to worry about the real structure and you're back in the complex Hilbert space picture. So, so you will not get elements in the real K-theory, you will just get elements in the complex K-theory.
I was under the impression that if we don't put any information about the space or on the dynamics, then we will be talking with time evolutions which are generated from the full B of H. And in that case, the K-theory should be trivial.
I mean, in some sense,
we still land in
yeah, it's this assumption here that really is kind of where the non-trivial topology comes in, or in this case, or in the or this assumption basically. So even though the BDG Hamiltonians can just be in B of H, they're close enough that their difference, that one is a compact perturbation of the other, basically.
Good. Thank you. Now it's a
it's a relative classification. I should have emphasized that. Sorry. There's always a base point, or there's always a pair, and you're just looking at the relative invariant.
So, Antonio,
I think Ralph has had his hand up for a long time.
You wanna read the question? Ah, Ralph. Okay.
Ralph, right. Okay.
When you put the C-star algebra A, it seems to me that you are kind of adding the quasi-momentum as a classical extra degree of freedom, but that the interaction is only among things with the same quasi-momentum, so to speak. So you have, so if you don't put the C-star algebra A, then you would have kind of a one-point system. You get just a Clifford algebra in the end. So it's like the stuff we learned yesterday. So it's kind of, there's no topology, it's just over a point. And then you put a C-star algebra A to kind of now do a families version of things over a point. So now you have a family of these interacting theories, but interaction is only among electrons with the same quasi-momentum. I'm wondering, is this actually what you want, or is it reasonable to assume that electrons with different quasi-momentum are kind of can't interact because they're moving so differently, or is it just because you can't do anything else?
I mean, it is partly the second reason, right? I don't know if I'm qualified to I think if this is physically reasonable or not.
Yeah. This quasi-moment picture only comes up if you have periodicity, right? Otherwise, you don't have this.
You want to put a row C-star algebra. I mean, here you could take any C-star algebra A. It doesn't really matter which one you put. But
yes, so
to that point, you had really something over a point. So it was really just a Clifford algebra that you got in the end. There was no further topology. And you put in topology at this step, and you can put it in using functions on your favorite space or using something else. You can put in, of course, these cross-product algebras that Belisar introduced. Anything is possible, but then this would still be kind of decoupled from this interacting part of the theory.
Yeah,
which part?
I think that's true.
I think what is defined here, this A defines the algebra in which you are allowed to do the deformations of your system. So it's the algebra, how far you can wander from the reference state omega, and that's what algebra A sort of
yeah, that's one way to think of it.
Accounts for. So it's how far you want to go from the reference state, and you quantify that through the algebra A.
Well, so A replaced the compact operators here. So in the beginning, we had the compact operators. Now we took a C-star algebra A. I didn't think it through, but if you took here continuous functions on the space, would you really get just the family of these kind of second quantization Fock spaces, or would topology
I mean,
interact somehow?
Yeah, I mean, when you start making these assumptions, then you really start losing the connection to the actual Fock quasi-free state, right? Because Well, or maybe I should be more careful and say that, okay, I don't yet know how these types of assumptions sort of play or affect the GNS state of the whole self-dual car algebra, right? I think that's a slightly separate question, but possibly still worth considering.
So in a real example, I think the hard work would be to calculate this algebra A again.
Yeah, in some sense, you take your favorite, right? the row algebra or something like that. And maybe the row algebra then gives you this sort of interesting connection to K-homology, which is this last remark, which I didn't mention, but would be interesting to consider as well.
Can you explain this last remark a little bit?
Well, it's just more like, so Ken Shiozaki, I once asked him, he said at one point was explaining that if you take SPT phases and you restrict to your allowed deformations to just be within free fermionic systems, then it should be classified by K-homology. I mean, so he's a physicist, so that was, I guess, just intuition at work, but I think it would be an interesting question to consider, and maybe the course assembly map gives you an interesting way to make that more precise. Because I mean, my indices are all landing in the K-theory of Cstar algebra, not the K-homology.
Yeah, I mean, I remember that in Kitaya's article, he also speaks about K-homology instead of K-theory.
I guess so. I mean, you can also just take the Poincare dual, right?
Does anybody else have a comment about this?
I have a question. Sorry. What about interacting systems? You expect some kind of persistence of this kind of results for weakly interacting fermion systems, for example?
I'm quite sure you could just do some basic sort of estimates where, so long as the interaction is sufficiently weak, then these results will not change. But I don't think that's super illuminating. So when you really have a proper interacting system, then it seems, as far as I can tell, the analysis is going to change quite substantially, just because, yeah, I mean, you no longer have any sort of Fredholm type assumption where you can sort of, where this assumption here really gives you a link to loops of Fredholm operators, which then gives you the connection to K-theory, and then you can generalize that notion. But when you're in the interacting picture, I don't see this type of behavior preserving in general. So it seems like it's going to be much more coarse in some sense.
Yeah, so let's say if we are in the Landau paradigm where we can connect the interacting system with the free fermion system that it will apply.
I guess so, yes.
Could I make a comment about actually this slide? So I believe if you're in class D, so that your equivalence class of this kernel of J0 plus J1 is going to land in Z mod 2, right?
Right.
Plus KO, the second KO group of a point is Z mod 2. And this appears to be simply what the physicists would call the ground state parity. Or a change of the ground state.
It's essentially the infinite version of that.
You get exactly the same.
Yeah.
So basically, that's the base case that one is actually thinking of and trying to generalize. Okay.
Okay, I think we have to stop the discussion here because we're going to have a next talk coming up.